Hello again. So today we're looking at a special case of what if the acceleration is constant. This leads to three equations called the uniform acceleration equations. In order to write them down, I need to tell you what the symbols in them are going to be. So suppose I have a car moving along a highway, and I denote its position along that highway. And at time t equals 0, it's at position x sub 0, or sometimes we call that x naught. Naught is another word for 0. And at some later time t, it's at some position x. And also at this time 0, it had some velocity v0 or v naught. And at this time t, it has some velocity v. Now using those symbols, these equations become v equals v sub 0 plus at, x equals x sub 0 plus v sub 0 t plus 1/2 at squared, and v squared is v sub 0 squared plus 2a x minus x sub 0. So I'm not going to derive those, they're derived in your book, and we're just going to take them as given. So again, just to remind you what I stated here in these equations, the sub 0 means at time 0. So this is velocity at time 0. This is position at time 0. This is velocity at time t at position x. So let's practice using these equations, and then you'll practice them in your homework. So again, using a car as an example because it's easy to picture. Let's suppose I have a car and it's moving with an acceleration of 2 meters per second squared. So it's moving, it's down the highway here, and it's moving initially with some v0 of 20 meters per second, and it's going to move down the highway a little further and apparently get squashed as well. And down the highway a little further down, it's moving now at some v of 30 meters per second. I'm going to ask a series of questions about this. One, how much time does it take for that to happen? How much time to increase its speed from 20 meters per second to 30 meters a second. So that's our first example, how much time to do that. So I'll look at my equations. I need an equation with time in it. I'll look at this one has time in it, but to use this equation I would have to know the final position, and I don't know that. So look at this equation has time in it, has initial and final velocities. I know both of those things, so I'm going to use that equation. V is v sub 0 plus at, t is what I want. I always solve algebraically first before you plug the numbers in. So this says t is v minus v sub 0 over a. So v is 30 meters per second minus 20 meters per second over 2 meters per second squared. And just to save us time on the video, I keyed that in already, and that is 5 seconds. So we now know that to go from 20 meters per second to 30 meters per second with this acceleration, it took 5 seconds. So we now know that this time is 5 seconds. Let's ask another question about it. Let's ask, how far did the car travel during that time? So if we let this position be x sub 0 equals 0, we now want to know what is x, how far. So we need an equation with x in it. This one doesn't have an x, we can't use that. So we can use either this equation or this one. Let's try that one. X equals x naught plus v naught t plus 1/2 at squared. We'll let x naught be 0 just by choice. V sub 0 was 20 meters per second times 5 seconds, we've decided, plus 1/2. A was 2 meters per second squared. T was 5 seconds squared. And if we key all that in our calculator, I did it already to save time, we get 125 meters. So it traveled 125 meters while it was speeding up. We could have used this equation. We could have said v squared is v naught squared plus 2a x minus x naught. X sub 0 is 0. Algebraically solving this for x, we get x is v squared minus v naught squared over 2a. V squared is 30 meters a second squared minus 20 meters a second squared over 2 times a was 2 meters per square second. And if you key all that in, once again, you get 125 meters. So it checks. We get the same answer. One more example from here. Suppose it keeps speeding up and it's going 50 meters per second. What is the acceleration to slow from 50 meters per second to a stop? So I can use any equation in the sense they all have a in them, but I want to find a. I've got 50 meters a second, and when it stops, v is 0. So I want to know a. So I'll look at this one. To use that one, I would have to know the time. To know this one, I would have to know the time. So let's try this one. I need more information. To slow to a stop, I either need to know the time or a distance, so I need to finish the question. Slow to a top in 200 meters. I didn't have enough information there. So now that I know that, let's use this equation. So I've got v squared is v naught squared plus 2a x minus x naught. Again, we'll just let x naught be 0 by choice. That's often true, but not always. So solving this for a, we get a is v squared minus v naught squared over 2x. So this is, v final is now 0 because it stopped, 0 squared minus 50 meters per second squared over 2 times 200 meters. And I keyed all that in, and that gave me minus 6.25 meters per second squared. It needed to come out negative because it was slowing to a stop. So this is an example of using these equations. You'll get to practice them some more in your homework. So enjoy.